Dirk Englund from MIT, talking about photonic systems for quantum information and physical AI. I get up after 25 minutes, talk should finish at around 30 minutes, and then we have still discussion. Take it away.
Super.
Thank you.
Thank you so much. It's great to see you all. Great to be back. So, yeah, I will tell you a little bit about some work we've been doing in using physics for compute, in particular for machine learning and in quantum computing. And I was reminded by Dimitri's talk how incredibly difficult it is to think through all the possible choices of how you could take one thing, GUI's thing, and then how can you, the infinite complexity, right, of potentially constructing a trial, and then you want to evaluate, is this thing, that machine that you built, is it good at something, right? Take a data set, apply it to it, and so forth. And this is an unsolved problem. It's a NP-hard problem, the combinatorial optimization. So I will try to tell you a little bit towards the end of how we might be able to simplify that a little bit with the use of AI. So, but we have to have a playground in which we can evaluate what we do. And for me, this playground is chiefly in quantum computing and networks. So what you see here is these bright spots here. These are individual atoms cooled by laser cooling techniques to microkelvin temperatures. I like to tease my friends at IBM and so on that this is 10,000 times colder than a Dill fridge. And then you can manipulate the internal state of these atoms by optical techniques. So optical addressing, so the optical interfaces here that I'm indicating here, they drive the internal state, the hyperfine state of the electron and nucleus. And that's how we talk to our memory. So our wires are optical in nature, and that's one area where, in particular, we're trying to build systems to make this wiring more scalable. And what I show here on the right-hand side is a solid-state analog of that kind of system. In this case, it's these are atomic defects in solids, and their electronic structure, the hyperfine structure, is similar to that of atoms in free space, except that you don't have to have a tweezer to hold them in place like you do here. But here they're held in an atomic lattice, in this case of diamond. And so the benefit is that, you need less stuff to hold it. It's solid state, but the downside is that it's also more decoherence and more complex. But that's our playground. And in building tools for these kinds of applications, I have realized in my faculty career that it's actually quite similar to some of the neuromorphic computing tools that and ideas that people have been developing. And so for me, it's been a really interesting 10 years or so since we started to apply methods that we originally developed for AMO applications to machine learning applications. And so, but all of these things are computing machines. And so it's just, I think it's useful to think, just like, what do we mean by a computing machine? Well, it's supposed to be a way to map an input to an output. And so suppose your input is some x and you want to map it to an output y. Then we can build a machine that is parameterized in the makeup of it by some vector theta here to approximate y. Okay, so how good is this machine that we build? Let's evaluate it on something. Let's evaluate it on a data set of pairs, input and output. This is the desired output again. You have pairs of x and y. So like one pair could be, x could be 2, 3, multiply. And the desired output is the multiply operation on 2 and 3 would give us 6, right? So we could have that in there if we want to make a multiplier machine, or perhaps a prime number factoring machine, or a machine learning machine that like does inference between cats and dogs. So we have inputs of images and labels of cats and dogs. right? So we have some data set, and we can give these examples to our machine and see how well it does in approximating the desired output. So what's the distance to the desired output with respect to the actual machine's output? And here, so you, right, for different things, you will define different loss functions, like cross entropy or something like that. And then you have, importantly, and this is like the point of this talk here is, and really in large part the workshop is you conventionally you will implement this here in terms of a program that runs on a computer like my laptop. But we want to think beyond that, right? Some of the parameters in here are not just software, some of them are hardware choices. And we want to see, hey, if you replace my von Neumann computer that's architecture that's built in a CMOS architecture with something else, could we do better at this cost function? And so let me be specific. So here, I want to show you an example of a machine. So as a machine is a cell phone, and I asked for an exploded view. That AI, you know, is always hallucinating. Not an exploded engineering, there we go. Exploded engineering view. Yeah, so frustrating. So yeah, the machine here, this machine, your cell phone, it consists of, like when you think about it abstractly, what is it made of? Well, some teams of people, they decided a number of choices. They decided that they would give for this particular pixel phone, it would give it a display with a display dimension of 6.1 inches, this number of pixels. It's built on some technology, a CPU that's running at 3.78 gigahertz, and etc. And so altogether, we can just put all of these choices into an array, into this vector rather, and there's some integers. That integers denote, for example, is it made of silicon or of gallium arsenide, the transistor? So it's one or the other, right? And then some continuous variables, like what is the transistor gate length, and so on. So I find it interesting to think about all kinds of stuff when I look around, like how big of a vector does that take to build, you know? For example, I take a clock. Well, I know a clock already is my prior. I know a clock should be either digital or analog, and so this one is an analog clock. So there you go. That's a 1, let's say, in my vector entry, and then it has some dimensions, etc. So I could probably put the fact that it is a clock, knowing that this is a clock on the wall. How large of a vector do I need to reproduce that exact clock? Probably not very many entries, like 10 or 100, probably 100. With 100 entries, I could, knowing that it is a clock, that I could say, oh, this is this clock, and I could probably reproduce that particular wall clock that you have there, right? With the phone, so how many parameters are there that dictate the engineered design? Not so many physics-wise parameters, maybe a few thousand or something like that. But they're not continuous. I can't differentiate on them, so it makes it hard to optimize how to make a machine. But then I also have on this machine, I have the operating system, I have the software, and perhaps some machine learning. Maybe a deep neural network is running on this, or a transformer, and that would be thousands of real numbers. So really, this vector here is like, thousands of billions of real numbers. This vector here is a very, very long vector in terms of the software choices, but then quite a tiny vector in terms of the hardware choices. But because it's mixed integer optimization, I can't optimize on it. So the best I could do is maybe try to represent it first into a mathematical problem, and then if I can at least formalize it, then I could try to see how well I can do an optimization. But even that is hard. So this is sort of like the point that I want to get across in this talk here. So let's look at a particular example. So now I have a loss function. This loss function is of the following type. So I want to map an input which is taken from the natural numbers, and I want to stick it into some machine, and I want the output the output has to be a product of prime numbers, which each can be raised to some other integer number. So, right, like you might have 2 times 2, so it would be 2 up here, to factor that number. And then the cost function is equal to 1 if the output of the machine is not equal to the input of the machine, right? If the prime number factorization did not succeed, and otherwise it's 0. Okay, so the cost function is very spiky. It's it's flat, and then there's a single 0, and then it's back to 1. And so that indicates why oftentimes it's so hard to optimize the makeup of these kinds of machines. The machine here for creating a prime number factorization thing. But let's take a look at a particular example. Like my computer here can take that number and factor it into its prime factors. And it takes, on my Mac M3 computer running at this speed, it takes about 5.6 microseconds to give that number. So here, the function is this. The function is designated by the loss function. And the shape of it, and the machine that actually makes it, it has this emergent property that I care about now. I care not only that it does the function I want it to do, that it breaks a number into its prime factors, but I also care that it can do this in a reasonable length of time. So I can compute I care about this emergent property of the machine, not the function itself, the runtime. So people have been making these von Neumann computing machines, von Neumann-based architectured computing machines since the 1950s or so. And here is the progression, the amazing progression that gives us today's computers. So we make choices that we build these machines largely using 3-terminal switches, transistors, and so here nowadays we're at my phone, or so has some about 1,000 million 3-terminal switches per millimeter square. And that gives me some 10 billion or so switches in a conventional CPU. And now so that's the makeup of the machine. Now how about this emergent property that I care about for my compute function? Here I estimated the time it would take to factor a bigger number, a 1024-bit number per year, the rate of factoring 1024-bit numbers per year per kilowatt. Of course, you can dump more compute at this, and then you can make it faster. So here, for instance, for 1 kilowatt, it would take the rate of factoring these numbers is about close to 10 to the minus 3 numbers per year. So it takes about 1,000 years at 1 kilowatt of power to factor a number of this size. Okay, so you might say, this seems pretty safe. E-commerce that relies on prime number factorization being hard should be secure, but wait, there are some people who would care a lot, and they can throw some megawatts at this. And even with a megawatt, actually, this doesn't look so secure anymore, because when you take that number and you multiply it by 1,000 kilowatts, you see you're at about 1 prime number factor per year, or even less than that. So this is the reason why people have adopted already some 15 years, 20 years ago or so. Our cryptographers were wise enough to foresee the scaling trend and said, we gotta switch to something else. And nowadays, actually, we use a 2048-bit encryption. And so for that, you actually have, it's just twice, the number is just twice as long, but the time to factor it is 1 billion times longer, okay? That's because of the inefficiency of our known, thus far, prime number factoring algorithms. Okay, so you'd say, hey, that seems secure. Well, first of all, you could just, you could extrapolate here, but second, we don't know that there doesn't exist some classical algorithm that we simply haven't yet discovered that can do the factoring faster. And moreover, well, there may be other machines. So because we've been on this bandwagon to build better and better von Neumann architecture machines, but especially in recent years, there's been a tremendous interest in building new kinds of machines, like the ones that you all are working on, right? Like neuromorphic machines, quantum computing machines. They rely on different architectures, and for these architectures, we don't have the same assurance that it takes that long to factor the primes, for example. And so it's just, so it's what is the right machine for the function is what I'm trying to get at here. So, so the important question that drives a lot of my research there is it's really, I would say it's about this prime number factoring, because it's an interesting question. Like, is it possible to build a machine? Is it possible to make a number of choices of different materials and algorithms and so on, so that you could, within 1 year, factor the number of 2048-bit length? And actually, both of the whether the answer to this question that nobody knows the answer to this question, and if the answer turns out to be yes. Well, first of all, there's going to be some panic, and there will probably be a big stock market crash because a lot of our e-commerce will not be secure, and many other things won't be secure. But on the plus side, there's actually some really interesting consequences of that, like discrete log scaling and other computational complexity problems would have to be rethought. It could be much easier. And if the question turns out to be no, you can't build such a machine, so that means like one of the companies that I co-started will not make it probably, but that's okay. That's fine because it's also super interesting, because so far we think we can make the machines. If you take like 100 physicists, 99 of them would say, yeah, you could probably build this machine. But if it turns out to be no, it's actually even more information, right? Greater entropy. So that has some really interesting things about how physics works and so forth. So to me, it's really interesting to build, to try to answer this question, like, is it possible to build such a machine by any sort of physics allowed methods? And that's the first question I want to talk to here. And the second question is, is what if you string these machines together in a network? What kind of new things can you do with it? And in particular, here in fact, building these kind of quantum computing machines, it's emerged that you have to do a lot of sensing and estimation and so forth. There's lots of data, and you have to make decision on lots of noisy data. And here, machine learning is also proving to be quite important. In fact, like, it's likely that AI sort of methods will drive the next generations of computers, quantum computers, more and more. And especially when you have very noisy signals, you can actually win in pushing machine learning inference methods to the detector, to the sensor, to the perception part of the machine. And so this has been a big area for me, and I'll tell you a little bit about this in the second part. And in the third part, what I was getting at is the tremendous complexity in building these machines, really overwhelming, and just even to formalize a problem well, like, would it be helpful? People ask me like, oh, is this switch that you're building, is it useful for machine learning? And most of the time I have to say, I don't know, because I can't formalize the problem mathematically so that I can evaluate it, right? And so just building good models has been incredibly difficult, and I'll show you towards the end here whether AI can help us build models faster so that we can answer these kinds of questions better. Okay, so now I have 15 minutes or so left. Yeah. Okay, so first off, first question, Q1. Building machines to do something like prime number factorization. So people are hard at it, building all kinds of different machines, and here is a representation of the complexity of the machine represented in the non-classical system size, the size of a coherent subsystem. So for example, in a superconductor, you can have a large coherent subsystem. In many-body localization of atoms, you can have large many-body subsystems, but you don't have the control over individual particles to run arbitrary algorithms. Whereas on the other side here, you can have optical systems that have relatively small coherent subsystems, maybe 4 entangled photons. But it's a small number, but you can control each of them. And so what we want to do is we want to be up here, where it's possible to do large system size and high programmability. And this is sort of the holy grail, is to push machines to that region of phase space, and then the hope is that you could do things like You could make optimizers that maybe will allow us to optimize these mixed integer optimization problems that are so incredibly difficult on using the methods we have today. So in building controllers for these kinds of machines, my work chiefly focuses on controllers for optical fields and then for quantum memories. And I want to just touch on this here. It's not really the neuromorphic computing core, but it is. It is using physical machines to compute in a different way, right? So I want to give you some flavor of where these machines are at, these quantum computing machines are at. And I also do it to introduce you to the hardware that I will use towards the second half of my talk in doing some machine learning and perception and so forth. So here I want to start off by showing you again this image that I had in the first slide. This is actually not from my group. This image here was taken in the laboratory of Mikhail Lukin at Harvard University. But at MIT we have now constructed a test bed so that we can try out different kinds of optical control and microwave control systems on these kinds of Rydberg quantum computers. And that effort is led by Adrian Manson, who was visited, for example, at the MPL before and works with a number of people in the area here, actually. So what we're showing here is these bright spots. Every bright spot is when we send a particular laser tone at it, it fluoresces, and that's what you're seeing here on a camera. And each of these is one and only one atom. And if it's in the different internal hyperfine state, then it's dark, and you don't see it here. So this is these atoms here. They can be arranged using tweezers, so you can arrange these registers that are perfectly spaced and so forth, no gaps and so forth, and then you can arrange them. To perform gate operations. So here, first you can internally control the state, and this is work by this team here at Harvard and at Clara and Caltech and a couple of other places. So they can then use these tweezers into which they've encoded qubits via optical fields to control the internal hyperfine state, and then you can bring two atoms close to one another, and you can pump the electrons into an almost ionized state, a Rydberg state, where you then have a strong dipolar force between these poofed up Rydberg atoms, and that gives you a conditional phase gate. The reason why people are moving these around is so that you can apply gates between chosen atoms. Okay, so then your circuit consists of moving these bits over here, interacting them here, moving them to somewhere else, etc. And in this way, it was possible to encode some logical qubits to do error correction at quite a surprisingly lower overhead than was previously thought necessary. And the same author, first author of that paper, is the last author of this paper. And here it's interesting. Here is what it would take to build a machine to solve the 2048-bit factoring problem. And this is a big surprise. If this is true, it's a big surprise, and it caused a lot of excitement, and that with only about 11,000 atoms, you could perform this prime number factorization in a matter of weeks to years with 2048 qubits, assuming reasonable and already demonstrated in separation physical error rates, and using a particular kind of quantum error correcting code that's relying on low density parity checks, or LDPC codes. There's one caveat there, that this LDPC code is difficult to there's some theory that still has to be done to implement that together with gate operations, but it seems plausible. And so it may be that this machine that we said might take what seems like 1 billion times away may actually become feasible. But nonetheless, you have to build a lot of control electronics, and so a lot of what we do, and this is now I can show you the actors in the second act here. What we build is in my team is we build optical control systems that would allow you to scale to these tens of thousands of control fields, and this is like what Dimitris was talking about, that we want to have, for machine learning also, you want to have a high number of precisely controlled optical fields that that maps nicely onto what we build for quantum computing applications. So you want, you want like 10 bits at least of precision, you want high dynamic range, you want high speed, etc. And so we make these tables and try to fill all the specifications by the machines we build. Sometimes we spin off these efforts into companies. This is a company I co-founded, and Clara now builds these visible spectrum photonic integrated systems that can scale to large numbers of channels with quite good extension, etc. And so here's just some examples of recent machines that we've built of this type. So here is a scanner, for example, in this piezoelectrically controlled waveguide that can show you a 100 by 100 pixel movie in the dimension that of just 2 iPhone pixels. And so we built lots of these scanners, and so that gives us some, in this case, each of these pixels can be modulated at 1 nanosecond on-off, and you can then, you have large numbers of control fields, not all simultaneous, but it's useful for certain kind of architectures. I'm going to skip over this, and I wanted to tell you about, so then when we use these kind of control systems in the field, we can really over the last 10 years or so, we've built machine learning systems that we can deploy into the field using the same kind of optical controllers. I'm going to skip over this, and I want to give you sort of the key lessons that I've learned in applying the kind of optics that I showed you a moment ago to the machine learning problem. And so one of the big lessons for us is in fan-out. So in machine learning, you oftentimes have the case where you use the same kind of model parameters over and over again. For instance, if you do on your phone, if you do an inference and you ask Siri some question, it will send your audio signal via wave file to the cloud, where it's then processed in one of these data centers. It takes a natural language processing model and applies it to your input. But this is the same program that's applied to all of the queries. All the natural language queries use the same program. So it seems somewhat crazy that why don't you have one server that supplies all of the inference machines with the same model? Because then you could maybe get rid of what turns out to be like the major compute load is the memory retrieval. Okay, so what about doing that? What about disaggregated memory access? And so this is actually, I would say, that idea was pioneered in earlier work where you could have models that can be stationary in some memory and then retrieved when necessary and fanned out, perhaps to many inference clients. And that was, it's one example of what we've built as these neuromorphic processors that either are stationary memories here in these photonic circuits, so that was already mentioned earlier before, and this one is the way that we really do ML inference chiefly today. We use temporal encoding, where we have weights, where we have output stationary architectures. So we have the weights, W here, and the signals propagating into a machine, and this machine performs integration, in this case on a capacitor, following a homodyne receiver. And that homodyne receiver, followed by a capacitor, performs an inner product between the input fields of the activation and one of the rows of your weight matrix. So, and this is all for free. You can stream in very, very long vectors here for X and for W. You only have to pay for it, really, once you sample the charge that's on the capacitor. That's really this analog to digital conversion. It has to happen only once. So you see, this is a fundamentally different scaling behavior, where on a conventional computer, if you do vector-vector multiplication, if the vectors are twice as long, you have to pay twice as much energy to compute. But here, if the vector is twice as long, to first order, you have to pay the same amount of energy to retrieve the inner product. And that has some interesting consequences. It means that, for example, in this theory work, we calculated what would happen if you made a computing machine based on this principle. And if you compare it against a conventional von Neumann architected machine, that machine would have to expend an energy per multiply accumulate, shown here in terms of joules, that would have to scale down to be able to keep up with this kind of neuromorphic machine. For relatively large problems, like fully connected 1,000 by 1,000 matrices and so on, a von Neumann architected machine would have to beat the Landauer limit, or like the thermodynamic limit of computing, which it won't. And so you have an example here where this kind of machine built on a different architecture could do things that no conventional machine could do. And so then we've built a lot of, really our work recently has been about building out hardware that we can error correct on, so that we can try out these techniques. Because, hey, if this is so good, like, why don't you have a, if this is so, why isn't everybody doing that? What you're saying? Well, the thing is that there's a lot of there's known unknowns that we can compute, but there are many unknown unknowns that we don't know. And so we do experiments and then theory to try to understand the problem better, so that we could say, well, if you put $1 billion into building a big machine, then you could it would be this much performant or so. So here is an example where different kinds of architectures. I don't have the time. I think I have to wrap up here, but I wanted to share this. So different samples, like what if we build a machine this way, or then that way, and then you learn a little bit along the way. So one that I wanted to point out in particular is here is something that for me was kind of new. Is what about a different mixer? What about, rather than using optics, you use the mixer that you have in your cell phone? Because when you receive a cell phone signal at 3 gigahertz or so, there's a mixer in there naturally that mixes your local oscillator with the signals coming from the cell phone tower. And so what if you modulated the local oscillator, rather than having a sine wave as a local oscillator, what if you modulated to encode your local inference problem? And I'm showing you here a video of that device in action. So this here is, we have a transmitter and a receiver, and this is now all happening in the radio waves, and doing the same kind of multiply accumulate onto an integrator, and it actually it works. So we can stream the model parameters by radio waves onto a RF receiver, just like in a cell phone. And we've been able in this published work to reduce the energy consumption per equivalent multiply accumulate by 3 orders of magnitude. Okay, so why doesn't everybody do that? That seems awesome, right? Yeah, I agree. Well, but the problem is in the details. So then you have multipath interference. If I take my cell phone and I run it along here, I would see constructive interference, destructive interference, and so on. And then you see, when you start building these things, you're like, dang it, the theory isn't quite as simple after all. And then you realize new things, and you want to try to build better models to say, well, what would happen if I built a big system based on this? And so, in fact, in building these kinds of systems, there's been a number of startups that that have been spun out by my group that I've been involved in, and it's always sort of like the same thing. You try to build something, then you build it and you learn it, and you then iterate the cycle. And because we don't have the ability to make very good models numerically, this has been oftentimes much slower than it could be in principle. And this is, so what I want is, like, every optics setup that I have in my group, I want to have a good digital twin of it. Now, you know, if you've tried this, how long it takes to take your optics setup and you convert it into a 3D model with ray tracing and so on. This, in our case, it takes us about half a year or something like this to get to this. Right? But you could say, hey, this AI, isn't that supposed to be so great? Why doesn't your AI do that? And well, normally if you ask your AI, hey, build a model, a ray tracing model of this apparatus, you can give it tons of photos. I've done this. It doesn't work. It hallucinates and it goes off on a deep end somewhere. But if you build into it verification along the way, it does start to work. Okay, so you have to build in good verifiers. And so really, this is the last point. Oh, actually, Axiomatic is sponsoring this conference, I think, in part. Does that give me like an extra 2 minutes? So then you get very obsessive about trying to replicate, to make models of stuff. For example, let's make a model of this beautiful paper by one of my colleagues. And then you see, then I rebuild this paper, but with a verifier. I run some numerical verification or symbolic verification to try to rebuild it. Then you go to another work and you try to rebuild like the claims of a paper. For example, this paper, this is a good one. This is an editorial, and it points to some other papers that are quite interesting. And so here I have this position paper by Dimitri, and then I will have the AI explore your paper here, Dimitri. And but the paper is quite short, so I could have read this. Oftentimes I'm like daunted by reading like very long papers. But this one was short, but nonetheless I put it in, and so the AI started to dream about physics and the stuff that you have in there. So does this run? Well, the thing is loading. I also took another cool paper here. This is this one. And this is one of Florian's recent papers. And I try to rebuild that. And I haven't found an error yet, but I'm trying. I'm trying to find errors. And oftentimes I do find errors. A lot of time it finds a flag, and it's not an error. It doesn't know, but it does say it's not validated, right? But sometimes it finds an error. So I'm trying to find errors in you guys' papers. This is a lot of fun. So you try to build models of things with verification. And actually, that does work pretty well. And when you have verification, you can then also, with the feedback, and you can also then say, hey, what about that grad student who's not getting my optics aligned? What about trying an AI instead of that? And so here's a robot arm, and it had to have this particular contraption to rotate the knobs there. But it's actually reasonably good at aligning optical. Well, see, there it aligned better. But it has to move back and forth. It's still a bit clumsy, but the thing is that it's look at this. You have a robot. This is a cheap robot arm, but nonetheless it can move something to a precision of sub-micron because it has feedback. In this case, very good optical feedback. And then you can have fun, and you can have other kinds of robots do the same thing, But it's all the same. So you want to have a good physics model. These are all model-based optimization things. So it has a model of the little setup, and then it can try to grab the knob and try to minimize its cost function. So that maybe is a way to make the model building faster, because now with model building you can interact with something, try it, and then update your model and so on. So okay, this is in summary. I want to just I've shared with you some of the main points I've learned in using these physical control systems and applying them to deep learning applications. But I've also learned to appreciate these 2 points by people much wiser than I am. Jan LeCun said, to reach true AI, we need to build machines that learn models of the world in a self-supervised manner. Let's connect robots to our apparatuses. It's a lot of fun. Claude is very good. Scary? It's like it cannot land a laser better. Or maybe, okay, now it's got a laser. Okay, you're right, it is scary. And the verification principle by Rich Sutton, he said that an AI system can create and maintain knowledge only to the extent that it can verify that knowledge itself. And what's cool about our kind of field is like in math and in physics and electrical engineering, it's so much easier to verify stuff than it is in harder disciplines like biology and so on. So I'm actually, it's pretty exciting time, and sorry for going a little bit over. Thank you.
Thank you very much. Axiomatic is sponsoring our poster prizes.
Yeah, so thank you. Great talk. A lot of was going to ask you about the quantum stuff. I visited this lab at Harvard by looking.
Yeah.
I was amazed at the number of acoustic things. It was like a incredibly complex thing, and it was doing like a single gate or something simple. Forget exactly what. But the complexity of building these things and entangling them and maintaining them and addressing them seemed to be overwhelming to me.
Right. Yeah, I mean, so an optical setup, like these AMO setups that we're basically copying or like replicating a setup like this from Mikhail Lukin and others. It has some probably tens of thousands of parts.
Yeah,
right?
Exactly.
So one thing is that they're made sort of there are only a few copies of it. There's a few groups who make that, and then so we only evaluate like these vectors like super sparsely. So we know, one thing we know for sure is that the machines that we build are far from optimum, right? There's very little variation. So one would be, let's have 1,000 times more groups build these machines, try variations, and that's not going to work. So the other way is let's make good physics-based models and bring them into a virtual environment. Then you could swap things out virtually and rebuild it and try that. Even there, though, plane manufacturers have engineers, hundreds of engineers who make good models of an airplane, fairly good models. They're often, but even they are known to be faulty. But we have a few students who build this. So it's impossible. I've tried this for a very long time. So really, so this is why I feel like it's so necessary that we have more automation in the model building itself. But then even I think real engineering setups systems like an automobile and so on has another 2 orders of magnitude more parts, and so you have to bridge. You have to make much better models to build machines consistently and to make use of your data consistently and to make choices from an informed basis than we have today.
Fabrication pathway, because the way they do it, what I saw there was just like like I showed the table, they put the acoustic modulators, and there's thousands of them.
Yeah, people do use microfabricated optics, right? But then when you make it microfabricated, the choices are more baked in, and because you don't know the choices being good, it becomes even harder. But if we knew what to build, I would say then there would be much more effort on actually making it miniaturized and so forth. But people don't yet know what to build. So that's really, it's more exploratory. Yeah.
Thank you very much.